All right, so here we go. So in last chapter we were talking about this chapter what we didn't finish, right? We were talking about acid and bases, and if you want to kind of like recap, what was the acid and bases? The acid was anything that releases H pluses, right? And we gave an example of acetic acid and hydrogen chloride because they both gave H pluses. Um, and if you look at the acid is pH is below 7, right? If you look at the base, on the other hand, they are releasing hydroxide ion, OH ion, right? Hydroxide, and usually, not usually, but all the case, pH is going to be larger than 7. And the relationship between the pH and pOH, we said that if you add them up, you're going to always get 14, right? This is how you can find one. If you have one, you can find the other one. And also, we were writing the pH by using the negative log of the hydrogen ion concentration, right? Same thing with the pOH. If you get the negative log of the hydroxide ion concentration, you get the pOH. And I think we did like a couple of examples, right? Like that. So if I give you the OH concentration or hydrogen ion concentration, you should be able to get the pOH or pH, right? And then we said that we are going to be using like not like with too many significant figures, but we're just going to use like 10 to the power, right? And the rule was that whatever the number on the exponent is going to be your pH or pOH, right? So that's where we kind of like left off, I guess. Any questions on that, everybody?
I just have a question. Like, I remember on the quiz it says like there's something about one of the elements is oxidized and then one of the elements is something else. I was confused on that. Like,
Oh, the previous chapter. Are you talking about the previous chapter?
yeah, from the quiz, one of the questions it asked like what elements being oxidized and then what elements being
Oxidized.
well, what was the other one?
Oxidized.
Another one is
Reduced.
yeah. How do you know which one is which?
I see. Yeah, that's actually previous chapter. Yeah, but I can talk about it here real quick. And there was actually some update. I think maybe you noticed. I forgot to tell you guys, but I made actually a couple small mistakes, and thanks to Tim, he actually emailed me, and so you may actually see some changes. Some of you actually got higher, grade, but some of you actually get lower grade because one of the question I kind of like, choose the wrong answer.
Was that the one
Uh,
with the
huh?
balancing equation?
It was magnesium. Do you remember the magnesium reacting with the nitrogen? And then you were supposed to find the magnesium nitrite, and then you're supposed to find the coefficients.
Oh, okay.
That one was mistakenly, like, I picked the wrong answer. And there was another one, but that was kind of like a small minor mistakes. So back to your question, if you have this reaction, we gave this reaction, right?
Okay.
So if you look at the aluminum is 0, right? Neutral.
Yeah.
But whenever it reacts, it grabs a charge of +3, correct?
Yeah.
Because of this, like if you do crisscrossing. So if you look at the aluminum went from 0 to +3, right?
Yeah.
Okay, so what happened to aluminum? Did it lose electron or gain electron?
It gained.
Huh?
It lost electron.
Lost electron. Again, if you get like more positive, Thomas, right, you're gonna actually lose electron because you have more proton than electrons. Make sense?
Yeah.
So if you lose electron, then we call you like we in chemistry we said that you are oxidized.
Okay, so if you lose it, you're oxidized. If you gain,
Yeah.
then you're
And if you look at the oxygen, on the other hand, oxygen is actually If you look at the charge, it's now -2, correct?
Yeah.
And oxygen is also 0. But as you can see, it went from 0 to -2, right?
Right.
So did it gain electron or lose electron?
Gain the electron.
Gain electron, very good. So if you gain electron, we said that you are reduced.
Okay.
Okay. And there was a question about like which one is being oxidized and which one is being reduced. But at the same time, we are calling, like if you look at aluminum, right?
Mm-hmm.
If there won't be any aluminum, do you think the oxygen will be reduced? No, right?
There's
Because
nothing.
whenever aluminum comes to oxygen, it's causing oxygen to being reduced, right?
Yeah.
Therefore, we call aluminum a reducing agent. Like we call it opposite. Make sense? If you are being oxidized, right, you are a reducing agent because you are causing oxygen to reduce. Same here, right? If you are being reduced, you're causing aluminum to oxidize, so therefore you are an oxidizing agent. Make sense?
Yeah.
It's the kind of like the opposite relationship. So that's actually how the reaction works. You
So
can identify.
most of the time when there's a reaction, the metal is gonna be oxidized, and then the non-metal.
True. Yeah, that makes more sense. Yeah, I think that's a good analogy. Very good, because you know that the aluminum is metal, and we said that the metals are rich, right? And electron rich. And if you're electron rich, you're going to give away electrons, and therefore you're going to oxidize. But non-metals are going to gain electrons because they are poor, and they like electrons. Yeah, that's a good analogy. Okay, very good. All right, any other questions, everyone? All right, let me open up another whiteboard, and I think we can start. Let's get a clean shot here. Oh, I think this is the one that we use, I guess. I have too many. Is this one? All right, so now we are going to be actually reacting these acids and bases, okay? And let me get a good background. All right. Okay, so we're going to actually talk about acid and base reactions in today's chapter. I mean, the rest of the chapter. And so when you look at actually acid and bases, right? Whenever they react, we actually learn, right? Whenever we have an acid and base is reacting, you're going to get salt, right? That's what we learn. And again, this is a salt and this is a water, right? You're going to always get water. And this is a strong acid and this is a strong base, right? You can actually have, you can also reaction of strong acid with a weak base or vice versa, right? You can also have that. And whenever you do that, let's say like acetic acid and NaOH, now you're going to get actually, again, same thing, water, right? And then you're going to get sodium acetate, which is this guy. What I'm telling you this because, again, you can actually, by using the weak acid and the strong base, or strong base and weak acid salt, this is salt, right? And if you mix this salt with another acid and base, right, then you're going to actually create a buffer system, okay? So what is the buffer system, right? So buffer system is systems where the the sudden pH increase and pOH decrease is actually tolerated, right? So I'm going to give you an example actually from our blood, okay? So this is actually a real reaction that you are seeing in our blood. So it's CO2 plus, so CO2 is a gas, and then you have water, and then you have H2O3. This is carbonic acid. Okay. So this is again, by using the carbonic acid, right, our blood, because again, whenever we are talking about the pH, right, pH is the negative log of H pluses, right? So therefore, if you add like even a small amount of H pluses, right? Because let's say you add just 0.1 molar, which is not much, right? But as you can see, if you add it 10 to the minus 1, right, you are changing the pH 1 scale, right? If it's 1, it's going to go, if it's 2, it's going to go to 1. If it's 0, it's going to be, you know what I mean? You are changing the pH 1 scale, so 10 times, right? You are making the solution whether acidic or basic, right? Strong acidic or basic, like 10 times, right? And as you can imagine, our blood cannot really tolerate that, right? We need something to kind of like tolerate that pH change. And whatever we are using, again, we are using our blood is using actually a buffer system. And how the buffer system works is, right, imagine you are actually adding an OH here, okay? Imagine something happened to us and our like we ate something very basic, like I don't know what, like maybe some alkali or whatever, right? So as you can see, if you add OHs, right, OH is actually since you have a hydronium ion here, right, so it will actually react with this so that it will consume the OHs so that it's not gonna go up and down. Make sense? Okay. Maybe actually I can come back to this. Let me actually explain. I think this is going to be difficult to understand. Let me explain again, this is not on your slides, but I think we need to understand one principle here before we take a look at this. So let's, on here, let me just explain to you guys something real quick. Okay, so you probably haven't heard this, but there is this principle called Le Chatelier principle. I'm not sure if you've taken any chemistry classes, but Le Chatelier's principle. Okay, so what is the Chatelier principle is telling us that if you have a chemical reaction like A plus B going to C, okay, and as you can see, most of the reactions, and as you can see here, I use actually double arrows, right? So one reaction is going forward, right? The other reaction is going back, right? So what this means is actually this reaction is in equilibrium in all the way down here, meaning that like in some reaction, the equilibrium is going to favor the product. Like here in the acid-base reaction, I see, like if you can see, I use not double arrow, just one arrow, right? Because the reaction is favoring the product really, right? So the reaction is going very fast and you can get the product right away. But in most of the reactions, right, that's not going to be the case. There's going to be always some equilibrium between these reactions. Like you start from here, right? This is your product, and this is your reactant, and this is your product, right? And you want to make more product, right? You want to consume all of your reactants so that you can have like 100% of product. But in most of the cases, as soon as you start building up product, right, you're going to actually come and you're going to reach an equilibrium, okay? And whenever you reach an equilibrium, then you have to kind of like push these reactions to go all the way to the reactant, okay? And so what the Le Chatelier principle is saying that, right, if we disturb, right, so whenever it reaches an equilibrium, right, if we disturb the reactions in a way, the reaction is going to actually act in a way to release that pressure, okay? So what I mean by that is, if you can think about this as a seesaw, right? Let's think about a seesaw here. Right, and so I have my A and B here reacting, right? Okay, and then making C, right? They are in equilibrium, okay? So they reach an equilibrium, and let's say I am actually disturbing this equilibrium by, and again, the idea is you can actually control the reaction. That's the beauty of this principle, right? So the idea is, let's say you want to add more A to it, right? So while the reaction is happening, you are increasing the A concentration, let's say, okay? So, and I want to understand how the reaction is going to go for it. Is it going to go for the product side or is it going to go for the reactant side? Okay, that's what I want to learn. So as you can imagine now, I am disturbing the equilibrium, right? There was an equilibrium. The seesaw was equilibrium. And what I did was I added more A to it, right? I increased the concentration of A. So what happens here is, again, I add another A here, right? So this side now gets heavy, right? So in order, right, this side gets heavy. Imagine this is my seesaw, right, like that. This side is heavy. In order for me to reach an equilibrium, what should I do? I need to add more C here, right? Make sense? Because this side is getting heavy, right? So I need to add more C so that I can actually make an equilibrium again. Make sense? So I need more C. So this telling you that if you add A, right, in this equilibrium, while the reaction was equilibrium, if you add more A, you're going to force these reactions to go to the product side. Make sense? Because you need more C, because you disturb the equilibrium and you put some A here, right? And now the reactant is more heavy and you need to make more C to compensate that. Make sense? So the reaction is going forward, and so that you're making more C. Does this make sense, everyone?
Yes.
Yeah.
Okay. And same thing happens with the B, right? If I add more B here, if I add more B into the reaction, same thing is going to happen. This side is going to get heavy. And in order to compensate that, I need to make more C again. And the reaction is going to actually go to the right again. Okay. And you can actually take a look at the this from the C side, from the product side, right? And so how can you, right? If I now, let me erase this A and B. Okay, now I have B here and making C, okay? So now let's say I actually added not A, not B, but I'm adding C, right? I'm adding more product into the reaction because you know your product, right? Let's say in this reaction, and then you're adding more product to it. What happens if you add more C? Do you think the reaction is going to go to the left or to the right? Do you think it's going to force these reactions to go to the product side or to the reactant side?
Reactant.
Everybody?
I say product.
Okay, we have product, reactant. Anyone else? Right, again, if you think about the our seesaw example again, now I'm adding more C here, right? It means that which side is getting heavier, right? This side is getting heavier, right? So how can I actually, how can I compensate that? Right, now this side is getting heavier. You see that, right? So I'm adding more C on this side. So I need to put something on the reactant, right? So therefore, I need to make more reactants this time, right? Make more. So therefore, I'm going to force these reactions to go to the reactant side. Make sense? To the left, to the left. Okay. Now, as you can see, right, by adding some chemicals and or removing it, I'm going to give you the example of removing it. You can actually control the reaction, right? Which way the reaction is going. Okay. Another example that I want to tell you is, and this actually happens, if, you know, in industry, believe it or not, because again, whenever, let's say you are a chemical plant, right? You own a chemical plant and you are actually making C. Let's say this is a very important chemical and that you are selling, okay? And but the reaction that you are doing is an equilibrium, right? And so equilibrium means that whenever you reach an equilibrium, that's it. You produce your product, and that's how much you're going to be producing it, right? But since you are a businessman, right, you're buying A and B and making C. So the more you make C, right, the better you're going to be off, right? So you want to push these reactions all the way down to the C so that you can get 100% yield. Make sense? Because whenever we reach the equilibrium, that's it. The reaction is done. You get your product 50%, you know, more or less, and then you're done. So you want to push these reactions all the way down to the product, right? You want to react every single of A with every single of B so that you can get a high yield. Okay, so how can you do that? Well, there are actual systems, again, whenever they are designing the reactions, right? So imagine as soon as you create the C in this reaction, okay? While you are doing this reaction in the flask, let's say you are heating this up, or I don't know what you are doing, but let's say you are heating this up, and you put a system, nice system, so that while you are creating the C, right, you are kind of like removing the C, okay? Let's say you are removing the C as it forms. What's removing means? You are removing, right? So you are decreasing, right? You're decreasing the concentration of C while it's removed, while it's being formed. Make sense? So remember the previous question that I said? If you add C to it, right, the reaction was going to the left. So what happens, do you think, if you are removing the C in this reaction? Which way do you think the reaction is going to go for if you remove the C?
To the right, because you need more C.
Right? Make sense? Everybody's following, right? Now you are removing the C. Now, again, we have the equilibrium. Let's say you make the C and we have equilibrium, right? And then as soon as you make the C, and whenever you have an equilibrium, now you are actually taking the C away, right? So you have C here, but because you take away the C's, now again this side is going this side is going down, right? Like that, right? If you remove the C, like that. I hope it's gonna make sense, right? But again, this is not a good seesaw, but this is an equilibrium, and you have the C here on this side, and if you take away C, this side becomes heavy, right? Like that, right? Make sense? So if you remove the C, this becomes lighter, right? Again, this side is going to become heavier. You can think about that, right? Heavier. Make sense? So in order to reach an equilibrium, what do you need to do? You need to make more C so that you can have an equilibrium, right? This side is heavier. You need to put more C so that you can have an equilibrium. So therefore, the reaction is going to go to the right again. And again, by removing the C, right, you can actually force these reactions to go all the way to the right so that you can actually get more and more C. Okay? And again, this is there are actually real applications where you can actually apply this Le Chatelier principle. Any questions, everyone? Again, it may not be making sense right away, but if you can think about the seesaw, it makes sense actually. Do you have any questions on this? Everybody?
No.
Everybody's good? All right.
Yeah.
If you have any questions, you can always ask everyone. Okay. Don't be shy. All right. All right. So let's apply these principles then that we just learned to the buffer system in our body, and how this relay system works. Okay, and how it kind of like tolerates the pH, and on top of that, what causes like the so-called acidosis and alkalosis. Okay, and what's the reason of this. So if you look at again this is the reaction that's actually taking place in our blood, and this is actually how in most of the cases, if you have a carbon dioxide, this is how the carbon dioxide is actually carried out, right? It was converted to carbonic acid, H2CO3, and you know, depending on the concentration of the CO2 or H pluses, the reaction can go again. This means that this reaction can go this way, right? Depending on the each chemical's concentration, or it can go to this way. This is how you know, we can actually tolerate the again sudden pH changes. Okay, so let's take a look at the case. Each case is again, we have two cases here, right? And the first case here is, let's say you are a person with let me just write it down here. I'm gonna need more space. Okay, let's say you have actually a problem, a person with a hypoventilation problem, right? Hypoventilation. Okay, and hypoventilation, you know what it is? Hypo, right? What is hypo means in Latin? I think it means less, right? Hypo, less,
Yes, yes.
right? My Latin is not good, as you can see. So hypoventilation is, again, you're doing a ventilation, right? You're doing a breathing in and breathing out, and so you're actually breathing out and breathing out, breathing in less, right? Less than normal. Okay, so you're not really breathing a normal level. So you're less than the normal, right? So in that case, if you look at the CO2 concentration, right? If you're again doing a less than the normal ventilation, do you think you're going to have more in your blood or less CO2 in your blood?
More CO2.
More CO2, right? Because you are not breathing out normal, so therefore you're accumulating more CO2. Okay, so the CO2 concentration is going to be going up, right? And so again, we're going to take a look at this CO2 concentration, and then we're going to see how this increase in CO2 concentration is going to affect the pH. Okay, and again, this is the reaction. And so if you have increased the CO2 concentration here, right? So now, again, think about the seesaw here. I have the seesaw, and I have the CO2, and I'm increasing it, right? So I'm increasing the CO2 concentration here. So this side is getting what? Heavier, right? Heavy. So what do you think the reaction is going to go for it? Do you think it's going to go for to the right or to the left? To the product side or to the reactant side? Now we are increasing the CO2 concentration, right? We are disturbing the equilibrium, okay? And if I disturb the equilibrium, now again, I'm adding more CO2 here. And now this side is getting heavier, right? This side is getting heavier. What do I need to do? I need to put something here, right, on the product side so that it's going to get, again, equilibrium. Make sense? So where do you think the reaction is going to go for it? To the product side or to the reactant side?
Product.
Product, right? Very good. Now, as you can see, again, it's going to go to the product side. It means that the CO2 is going to react with the more, I mean, you're going to have more reaction going on, and then you're going to produce more carbonic acid. And because it's going to go to the right, you're going to have, what do you think is going to happen to the H plus concentration then, if it goes to the product? Do you think the H plus concentration is going to go up or down?
Up.
Up, right? Very good. Okay, so the hydrogen concentration or H plus concentration is going to also go up, right? Because the reaction is we are making more and more product so that we can reach an equilibrium again. See that, right? Okay, very good. So what happens then if the hydrogen ion concentration or pH concentration goes up? Sorry, H plus concentration goes up. what happens to pH?
Goes down.
It goes down, right? Because if you have more acid, more H plus, it means that you are more acidic, right? Makes sense, right? Again, there's an inverse relationship between pH because it's a negative log. So the pH is going to go down, right? Again, whenever you have a CO2 concentration goes up, pH is going to actually goes down. And this is actually where we call acidosis, right? Acidosis, and the pH is actually get a little lower than around like 7, I think 7.35, somewhere around that region. But as you can see, again, depending on the CO2 concentration, right? Our body is actually, again, by using this reaction, right, it can tolerate the sudden change of one of the chemicals, right, or CO2 here in this case, right, so that it can tolerate, the sudden change of pH changes. Okay, so this is one of the example, and what about the other one? The other one is whenever you have, let's say, instead of hypoventilation, now let's say you have a hyperventilation, and hyper is it
More.
means more, right? Like whenever you say like hyper kit, is like it's more energy, right? It's like more. And again, hyperventilation, whenever you do hyperventilation, you are doing more than the normal breathing and breathing out, right? You like imagine you kind of like work out, right? You kind of like ran 5K, and then now you're breathing in and out like so faster, right? So in this case, the CO2 concentration is going to go down or up?
Down, I think.
Down, right? Right, because you are actually doing more than normal, and now you are giving out more carbon dioxide, so it's going to go down. Okay, and so if it goes down, now the reaction is actually different, right? Now the CO2 is actually going down. So now if you look at your seesaw, right, now the case is different. Now CO2 is getting down, right? Down means this side is getting lighter now, right? This side is getting light there, and this side is getting heavier, right? So like again, when you think about lighter, now this is the CO2 side, right? Now this side is getting heavier like that, okay? And so what should I do? Should I add more CO to it or less to reach an equilibrium again?
You have to add more.
Add more, right? So how can I add more CO2? I need to shift the reaction to the reactant. Make sense? So now reaction is reversing, right? Because again, this reaction can go either way. So now H plus and bicarbonate, this is bicarbonate by the way, polyatomic ion, they are reacting so that they can make more CO2. Make sense? So if the reaction goes to the left, now it's going left, we are making more and more reactants, okay? What do you think is going to happen to H plus concentration?
It's gonna go down. I mean up. It's gonna go up.
It's going to go up, right? Very good. See, it's going to go up because now it's less acidic, right? It's going up. Remember, like pH 7 versus pH 2 or pH
Wait,
14.
doesn't the concentration go down? The
Sorry, it's
pH
going to go down.
the pH goes up.
Yeah. And again, let me just reiterate what we said, right? Again, the reaction is going to the left, right? So what does this mean? This means that you are actually reacting H pluses and bicarbonate. Imagine you used to have like 2 molar, let's say. Now, because these two are reacting and making more CO2, and so therefore the H plus here is going to go down. Makes sense? Because your product is reacting with itself, with another product, and making more reactant. Because we need more CO2 on the other hand. You need to help the CO2. Make sense? Does it make sense, everyone?
Yeah.
So the H plus concentration is gonna go down, right? And so now, what happens to the pH here?
The pH goes up.
Yep. If the hydrogen ion concentration goes down, right, because it's the negative log, it's gonna go up. Okay. And again, this is actually where we called, I believe it's alkalosis, right? Alkalosis. Okay, and the pH is gonna go a little higher than 7.45. Again, this is again by studying the chemistry, right? Even though there is some biological, effects on the body, right? If you know your chemistry, it helps to understand really like why we have such a pH change, like in acidosis and alkalosis. Okay, makes sense?
Professor, this is related to like blood doping, right? Like for athletes, like you hear about blood doping. Is it related to that? Like how they increase the CO2 concentration in their blood, like on purpose to be able to run faster or run longer.
Yeah, I'm not sure about that actually. I need to look into that.
Okay.
I know how doping works in like in more traditional way. They get like more like testosterones, right? So that our body actually produce testosterones, but they actually get like more like the outside testosterones, like the testosterones that they produce in the lab. And but yeah, there are like more sophisticated ways of blood doping. But I yeah, you might be right. Okay, so this is again how we can actually, again, by applying the Le Chatelier principle, we can really predict the how the reaction is going to go. Again, you can actually also apply heat to it, right? If the reaction is exothermic, endothermic, but we're not going to get into that. But there are again a lot of nice things that you can drive from the Le Chatelier principle. I really like this principle. You can apply to in reactions basically. Okay, so let's do a couple examples on this since we are here. Okay. So again, I'm going to have this reaction again, and let's say I'm just going to give you a couple scenarios, and let's think about where the reaction is going to go. Okay. So again, we are still looking this reaction. Okay. So we talk about all reactants, right? So let's take a look at the product side, and let's say what happens if I if you increase H plus concentration here, okay? And what happens if you decrease, or if you remove, let's say, if you remove bicarbonate ion? And can you predict where the reaction is going to go? To the right? How the equilibrium is going to be affected by this? So let's say you can look at the first case, A and B. Again, we are looking at the same reaction here. Okay, so what do you think about the first case if you increase the H plus concentration?
I think that if you increase it, it will be more acidic.
let's not talk about the acidic basic, but I'm just asking, where do you think the equilibrium is going to go? To the left or right? Right. How the equilibrium is going to shift? Do you think it's going to go this way, or it's going to go the other way?
To the left.
To the left?
Yeah.
Okay. Everybody agrees?
Yeah.
Right? Again, if you increase the concentration of H pluses here, again, now you're adding more more H pluses right here. So again, if you're adding, think about this here. So you're adding here. Now this side, the product side, I mean the reactant side get lighter, right? So you need to make more reactant to compensate, right? So therefore you're forcing, right? So you're forcing the reaction to go to the reactant side. Make sense? So yes, you're right. So it's going to go to the left. Everybody see that, right?
Right.
Okay, makes sense, right? Again, if you have any questions, guys, don't hesitate. And let's look at the second one. If you remove the HCO3, which is bicarbonate, now I'm removing the H3. I'm removing the bicarbonate, which is this guy. What is removing means? If you remove something, do you think you are decreasing the concentration or increasing the concentration?
Decreasing.
Huh?
Decreasing?
You're removing it, right? I have 1 cup of glass here, okay, and I remove 1 cup of glass. How much water do I have? I have 0, right? See, now in the screen you have 1 cup. I removed it. How much water do you have?
None. 0.
Right? None. 0. So removing means what?
Decrease.
Right? Decrease. Right? You're decreasing it. Right? You're getting like from 1 cup to 0 cup. Right? So just like that. Again, bicarbonate. If you look at the bicarbonate now, the concentration is going to go down, right? Because you're removing it. That's what it means, right? You're removing it. Okay. So what do you think the reaction is going to go then?
So that
If
means
you
it has
remove
to
the
go to the
bicarbonate
right side to balance it,
to the where?
to balance the equilibrium. It has to go to the right side.
Yeah, I can't hear you.
Can you hear me now?
Yeah.
Oh, I said it has to go to the right side to balance it because
Exactly.
if you're
Right?
removing it, it's going to make it lighter.
Yes, exactly. Okay. So now the product side is actually need helps, right? Because now the product side is actually getting lighter, right? And we need to make more, right? So therefore, the reaction now this time goes to the right, okay? So that we can actually compensate the loss. Make sense? Okay. All right. Any question with this, everyone? Okay. Everybody's good?
Yeah.
All right. Good. So let me open up my which chapter was this? Chapter 9, right? I don't really know the chapters. Which chapter is which? I think it was 9. Okay, so let's finish up this chapter. Are you seeing my screen now or no?
Yeah.
Yeah.
Okay. And again, we talk about salts, right? And again, we talk about buffer a little bit. And this is the buffer system that actually takes place in our system. And again, we talk about, you know, metabolic alkalosis, acidosis, same thing. Okay. Okay, now I'm going to talk about a little bit about this. These are the last part of the chapter, and you probably already know this, but you know this is actually how you know the concentration changes in if you have two different solutions, right? And and then we know that diffusion is whenever you have like solute here, right? Let's say you put kind of like a like a crystal, like a solid, right? And if it's dissolving here, then it's gonna actually like disperse, right? So that it's gonna actually get even to everywhere. This is what the diffusion is, right? So it moves from a high concentration to area of low concentration, right? If you have like, again, this is classic example, if you chop an onion in the kitchen, right, it's gonna slowly diffuse to everywhere because we have a high concentration here, and you know, again, the system, they want to be, we want to have equilibrium everywhere, right, in the whole room. So that's why it's gonna spread out to whole room. And if you look at the osmosis, though, osmosis is a little different. It's a special type of diffusion because it actually involves the passage of water, and also you need actually a membrane, right? Semi-permeable membrane, all right? And so in this process, because the solute, in most of the cases, is big enough and it cannot really move on, right? It cannot pass through, but the water can move, right? And and again, the idea is the same, right? We want to have an equilibrium. If you have a high concentration and low concentration, two different solutions, we want to have an equilibrium, right? We want to reach an equilibrium. So if I can give you an example, I'm not sure if you can read it. Can you read it?
No.
Let me blow this up. Now let's say you have these two solutions, okay? And so the first one is 5% sucrose, and sucrose is, again, we're gonna learn about this in the last part. It's actually a sugar, right? Disaccharide, and it's a large molecule again, right? It's not like a small molecule, and sucrose cannot pass through this membrane, right? But what can it, sorry, but the water, because we are in water, right? Because we are using solvent as a water, water can pass. So think about it. You have 5% sucrose solution here and 20% sucrose solution here. Which side is more concentrated? A or B?
B.
B.
B, right? So B is more concentrated. So again, we need to reach an equilibrium, right? So how can I reach an equilibrium, right? I need to reach an equilibrium, and the equilibrium is going to be supposed to be between 5 and 20, right? Somewhere in this percentages, right? So where do you think the water is going to go then? Like, do you think the water is going to go from A to B or B to A?
B to A.
To
A
A?
to B.
A to B.
A to B?
Yes, because you have more water in 5% sucrose.
Okay. And again, if you think about it, right, it looks like B is going to go to A, but again, I'm talking about moving water, right? Because sucrose is big enough because it cannot really pass. Sucrose cannot pass.
Mm.
If it can, it will be. But again, we are using this membrane. So this is the membrane, right? This is the membrane. So we have a membrane between them, and sucrose cannot pass. But as Magros was saying that, so you have more, right? This is more concentration and this is diluted. This side, A is diluted. So you have more water here. So because you have more water here, you have less water here. Same thing, right? Here, see, you have more water, less. So just like the diffusion, the water is gonna pass through here and move to the B, right? And by doing that, the concentration of this A is going to actually increase, right? And the concentration of B is going to decrease so that you're going to reach a same concentration. Make sense?
Yeah.
Okay. And so as you can see, right, the water from A is going to move to the water to B so that you're going to have larger than 5% here and smaller than 20% on the other side. Okay, it's again, it's nothing but a special, you know, diffusion because we have a membrane. It's the same principle basically. And again, whenever we read the osmotic pressure, then it's going to equalize, etc. Okay. And so whenever we talk about this, we also want to learn about like how the diffusion is going to affect our blood cells, right? So if you think about if you think about a solution where you have, again, if you have a hypotonic solution, let's say this is your blood cells, right? Can I write this? Let's pick up another color. Okay, so this is, again, this is the cell, blood cell, inside the blood cell, and then you are given a hypotonic solution to your blood cells. Okay, and what's hypotonic means? Look at the concentration. Which side is more concentrated?
Hypotonic means low
Low, right?
solute.
So it's a low concentration. As you can see from the dots, right? So the outside is less concentrated, right?
Yeah.
And inside is more concentrated. And the only thing that can move here is water, right? So what's going to happen then? So the water, right, from the outside, yeah,
The water is gonna go inside the cell.
yep. So the water is going to actually get inside the cell, your cell.
then
And
it's
as you
gonna
can see, your
increase.
cell is going to get bigger and bigger and bigger, right? And it's going to actually, we call this a hemolysis, right? And it's going to burst at some point, right? Whenever, you know, hopefully it's going to reach an equilibrium, but eventually it's going to burst, okay? And this is, again, the effect of the hypotonic solutions in your blood cells. And if you have a hypertonic solutions, and again, hyper means, right, hyper means high concentration. This is high. And now the opposite case is true, right? Because the outside is actually more concentrated and inside is less concentrated, right? So you have more water inside the cell. Okay, so the water is going to go out this time, right? So water is, you are losing water in a cell. And whenever you lose the water, then you're going to have a shrink, right? Your cell is going to shrink, and then it's going to cause crenation, in other words. Okay. And then we have one more solution called isotonic. And if it's isotonic, right? Isotonic means it's the same concentration. If you have isotonic solution, nothing's going to happen because the concentration is same for inside and outside, and there's no interaction because you already have an equilibrium basically. And you need to know kind of like these two concentration, right? So if you have 0.9%, again, look at the percent, we know percentages now, weight, mass, volume, it means that you have 0.9 gram in per 100 milliliter, right? This is what it means. Because if you do 100 times, then you get the idea, right? Hold on, guys. Where's my microphone? All right. Sorry, guys. Let me just blow this up again. And so again, if you are larger than 0.9, why I keep getting white? So these are two isotonic solutions again, right? And so if you are greater than these solutions, right? If you let's say give 5% saline solution, then it means it's a hypertonic, right? So as long as you know your isotonic solutions, you can know whether you have a hypertonic or hypotonic solutions, and then you can actually see the effect. Makes sense, right? Okay. Again, 5% glucose and 0.9% saline. These are going to be your isotonic solutions without an effect on the blood cells. And actually, this is when we were going to be on ground. We were going to do some dialysis, experiment, but unfortunately not. This is actually how our kidney works, right? And so we have, two kind of like a stream, right? And in one of them we have a high concentration and in the other one low concentration, and there's an exchange between those two molecules, okay? Yeah, it's the same thing that we said. And again, this is a hemodialysis unit. And as you can see, it's a very large machine, our kidney, thank God it's just like a small machine, but it's like doing a lot of work, right? And, I have some relatives actually who were using this hemodialysis, and it's like a pain. It does the job, but, it's not an easy job. All right, everyone. So I think that's going to be it for this chapter. That's my last slide. It was kind of like a long chapter, but we did it. I mean, I could have finished it in 1 week, but I think, it's not so bad that we can finish in 2 weeks. So do you have any questions, any concerns with this chapter? Do you have any questions, everyone?
I'm good.
Everybody's good?
Yes, sir.
Do you want to do a couple more examples with acid, base, or like anything that doesn't really resonate?
Yeah, we could do some more examples if you want.
Say it again.
I said we could do some more examples if you want.
Yeah, I mean, again, I have. We can do it. Like, which one do you want to do? Like, which side? Which part?
Maybe like show some examples of what might be on the quiz, and we could see if we could figure it out.
Yeah, again, the quiz is going to be similar to what we've seen, right? Again, so far, I don't think I made any, like you didn't see like any question, and then you didn't say, "Wow, like we haven't seen this," have you?
Every day. Every day.
Come on, Carlos. No,
Every day.
I don't like to make surprises. I kind of like ask the same question that I went to go through in my in my lectures.
So let me understand this as far as H plus. So the when H plus increases, it becomes more caustic.
More what?
When we increase H plus, that solution becomes more caustic.
More what? Cost?
Caustic, it becomes a base.
Not really. Actually, it's actually more acidic.
All right. So if we're decreasing H plus, it becomes a stronger acidic. I'm just trying to figure out when H plus, when we take away H plus, it becomes more acidic, or if we give it more H plus, it becomes acidic. This is where I'm getting mixed up.
Yeah. So Carlos, if you look at this reaction right now, right? So this is your acid, right?
Yeah.
And again, by definition, the acid means that you have more H pluses, right? I mean, sorry, if you have releasing H pluses into aqueous solution, then you are an acid. So if you have more H pluses in the reaction, it means it's gonna increase, the solution is gonna get more acidic, basically.
Okay.
Sense?
Yep. Yeah.
So if you have more H pluses, right, more and more, then it's gonna have more and more acidity. Okay.
Okay.
For the basicity, you need OH minuses. Again, these are two
minus
different things. One of them is plus, one of them is negative, right?
Okay.
So so again, same thing applies here. If you have more and more OH pluses, then it's gonna go. The basicity is gonna go up.
Okay. All right. So,
but I think you're mixing up with the pH, because if you look at the pH is the negative log of H plus concentration, and therefore, right, if the H plus goes up, because you are getting the negative log, pH goes down. Make sense?
Oh, okay.
So if you look at the pH, for instance, remember we talk about 0 to 7.
Right,
So
right,
pH 0 is more acidic than 7.
right, right.
Make sense?
Yep.
Okay.
Okay.
Because I can give you an example right here. Look at this. 0.01 molar, right? Let's look at this solution. And then second one, 0.0001 molar. Okay. So which one has a higher concentration here?
Number one.
Number one, right? So
Right.
you will expect this to be more acidic, right? Because you have more H pluses, right?
Yes.
Okay. And so if you apply this into the pH, let's calculate the first one pH, negative log of, and this is actually 10 to the minus 2, right?
Yep.
And so you get the pH of 2, right?
Right.
And if you look at the second one, look at the pH of second one, same thing, negative log. Now you have 1, 2, 3, 4. So it's negative 4,
Mm-hmm.
right? So and you
So
get
it's just
pH of 4.
4.
And that makes sense because this is actually much less concentrated, 0.00. How much is, as you can see, it's actually almost like 100 times, right? Not almost, but yeah, 100 times less concentrated. And as you can see, pH is going up. Okay?
Okay.
So
So
pH, yeah. mhm.
so number 2 is 2 times stronger than number 2.
Well, I think that's a good question. I think I answered. We kind of like went over a little bit. So that's a good question. So how much more acidic
Yes.
the second one comparing the first one? 2 times?
It's 2 times, but still less acidic than number 1.
Yeah, it is less acidic, but it's not 2 times, right?
Right.
If I ask how many times, right, because we are getting the negative log, you really need to look at the concentration of each. So you need to divide the first one to the second one. Make sense?
Okay.
And then you're gonna get, as you can see, it is actually 100 times. Make sense?
Yep.
If we ask, if we want to compare the strength of the acidity with how much more acidic, you need to really look for the H plus concentration, not the pH.
Okay.
Okay?
Yep.
All right. Any other questions, everyone? Everybody?
No.
No, I think that's good.
Let me just take a look at your quizzes right away. But again, back to Thomas. I think Thomas was asking. It is again similar like questions that we did over and over in our lecture, guys.
Okay.
And again, if you have time, if you can do your assignment, suggested assignment questions, well, that also helps. And it's pretty much more or less the same questions. So chapter 9, right? Yeah, so again, like we talk about, what was solute, what was solvent, solution, right? The meaning of this, you should be familiar with it. And we talk about the percentages, right? We talk about molarity. You should be able to do this. Yeah, maybe we can do 1 or 2 example with the molarity because you didn't do.
So are we doing the lab today? Because it's not due until next week.
Yeah, that's another thing. I'm gonna be assigning this lab today, so that you're gonna have a week to complete, because we just finished the acid and bases, and so you know what the acid and bases is now, so you can actually do your labs. Okay. Let me. Let me share my whiteboard again. Okay, so if I say, let's say you have, and this is like a hypothetical question again. Let's say you have 10% hydrochloric acid solution in water. If I ask what's the solvent here,
Water.
what's the solute here? Can you tell me?
Yeah. Yeah. The your solvent's going to be HCl and your solute's water.
10% HCl solution in water.
Oh, you want a percentage breakdown. Okay.
Which one is your solvent? Which one is your solute, guys?
The water is the solvent, right? No.
Everybody agree? Disagree?
Yes.
Water is usually a universal solvent.
Yeah, I mean, again, water can be, you know, like can be a solute too. I mean, you know, you cannot just say, oh, just because it's water, it's a solvent. But here, I'm saying 10% HCl solution in water, right? So 10% HCl solution in water. This means that you have 10 grams for every 100 milliliters of water. So in this case, again, your solvent is water, right? And your solute is going to be HCl. You're dissolving HCl in water. Make sense?
Yeah.
Okay. Yeah. You can go back and again review what was the definition of solute and solvent, etc. If you have like a soda, let's say you're drinking a soda, right? Again, what is the solvent in soda?
Water, carbonated water.
Right? The water is your solvent again, and whatever the soda is, that's gonna be the solute, like whatever, what kind of soda you're drinking, but yeah, but
Like
you get the
sugar.
idea. Okay, and let's do one or two examples because this was like 2 weeks ago, so that we can actually, you know, refresh our minds about the, remember the percentages. So let's say you have, okay, sodium, sodium chloride, polymers. Okay. Let's say you have 58 gram yeah, let's take a look at this two example, and I'm just going to ask you to find two things here. Okay, let's say you have 58 gram of sodium chloride, okay, dissolved in let's say yeah, I'm just going to make this up, but yeah, you can get the idea. Dissolved in let's say 500 milliliter of water. Okay, so I want to find out first, I want to find out two things here. First, what is the mass volume percentage of this solution? First thing. And second thing is, what will be the molarity of this solution? Remember the molarity? Molarity of the solution. These two things.
Is it 8.6%?
Okay, so let's take a look at the first one. So again, what's the mass volume percent, right? You are dividing mass over volume, right?
Yes.
And whenever we are doing the volume, you just make sure that it's actually in milliliters. That's the case. If I give you this in liters, you have to convert into milliliters, right? But here, I don't have to worry about it, right? And so the mass has to be in also grams, okay? So what is the mass here? It is 58
Divided by 500.
divided by 500
Yeah, 8.62.
times 100, right? So whatever the number here is, you're gonna give, I guess it's gonna be like around like 10% or so. Okay.
Oh, so then it's
Okay. You got the idea, right? I don't. I cannot divide this on top of my head, but
1.6.
but you get the idea, right?
Yeah.
Okay. So what about the molarity? I think the molarity might be a little bit challenging, but again, not so much. Molarity was, these are again two different units that we use to describe the concentration of solutions. So molarity was moles over volume. And in this case, the volume has to be in liters, right? We are describing molarity, how many moles in per, like in per liter of solution, of solvent, not solution, solvent. And so here, I need to convert also the mass to moles, right? I cannot just plug 58 here because that's a mass. Okay, so now let's find the moles. What was the moles of a substance? It was mass of the substance divided by molar mass, right? Right, everybody?
Yeah.
Okay, and so I have 58 gram of sodium chloride divided by, what's the molar mass of sodium chloride?
58.
58, right? I didn't give this to you, but you can actually find it by going to periodic table, okay? And adding this, sodium is 23, I believe, and chlorine is, let's say, just 35. So I think there is some significant figures, but it's okay. And if you add them up, right, you're just going to add them up. So if you have 1 mole of chlorine, it's 35. If you have 1 mole of sodium, it's 23. And if you add them up, right, that's going to be 58 gram per mole. So if you divide this, you're going to get your moles, right? So it's 1 mole. Everybody understand this, right?
So the answer for B is 2.
Okay, so now I'm not done yet because I have to plug this in here. So it's going to be 1 mole divided by now volume here. See, again, I cannot just put 500 here. That will be wrong because by definition, the molarity has to be in liters. So I have to convert this 500 milliliter to a liter as well.
0.5, it converts to 0.5 liters, and then 1 divided by 1/2 is 2.
So 500 milliliter is, right, again, I'm not sure how you are doing this, but you can, again, apply your conversion factors, right, because 500 milliliters times, you're going to use a conversion factor, and I need everything in liters. So 1 liter, I know that it is 1000 milliliter, right? And if you do this math, milliliter is cancel them out. And as Thomas was saying, it's going to be 0.5 liters, right? So it's going to be 0.5 liters. So if you do the math, it's going to be 2 molar. Make sense? Again, it's not going to be more complicated than these questions, okay? If I ask you the molarity, I'm going to give you the mass. You have to convert into the moles first, and then plug it in your formula to get the molarity. Okay? All right, everyone. I think we're good to go. I feel confident in you guys. Everyone.
Yeah. Okay.
Especially Carlos, in you.
Yeah. Okay.
Just review the material, okay? And, you know, go over the assignment questions. And yeah, should be good to go.
All right. So we have the quiz to do for chapter 9 and the lab to do for chapter 9.
Yep.
Due by Friday.
Yep. Okay. And I'm gonna see and check. There was one request for the time. I'm giving 20 minutes actually for each quizzes, right?
Give or take. Yeah.
How many questions are on this quiz?
On this one, there is 1, 2, 3, 4, 5, 6, 7. There's nine questions.
I need 10 minutes for each question.
No, no.
Oh my goodness.
Oh, I'm slow. You don't have no idea how slow I am.
Okay,
Can
I'm gonna
we
give you.
half an hour?
Yeah, 30 minutes is good, right?
Okay, I'm gonna make it 30 minutes then. Okay.
Thank
Let's
you.
make a deal.
Okay, that'll
Okay,
work.
so I'm gonna make 30 minutes, guys. All right, so it's 30 minutes. All right, so I think that will be it for today. If you have any questions, any concern, let me know. If not, I will see you guys next week. Next week, there's nothing. There are a couple days off actually on the week on the MCC calendar, but I didn't check. A couple, I think 1 or 2 Saturdays we are not going to be meeting, right?
I don't know. You tell me.
Where's my phone? I put it down on my calendar, but I wasn't really sure. I thought you guys know better because you like off days.
I think there's one like in the around the middle of March, like
March, yeah.
for spring break, like something around
Oh
like
yeah,
the
yeah. There's spring break, and then there's one more thing. Yeah. Okay, then.
fifth.
Yeah, I think we have time. Then don't worry about it. So it's not just coming up right away. Okay.
You're ready then.
Okay.
Thank
All right,
you.
everybody. Enjoy your weekend. I know it's
Thank
a
you, you too.
rainy day, but you can enjoy, I guess. And I will see you guys
Thank you.
next Saturday.
All right.
Thank you. Thank you.
All right. All right.
Bye bye.
Professor?
Yeah.